This lecture has to do with electron configurations, and the goals of this lecture are to understand the importance of electron configurations, to allow us to predict properties and reactivities of atoms and ions, and to learn how to be able to write electron configurations, and with those to identify valence and core electrons. In addition to this lecture, please make sure to read section 3.4 of the OpenStax textbook. Um, and this lecture really ties in with the major theme of the course about how structure affects reactivity and properties of atoms and molecules. So we'll start off with a little bit of background. What we should understand now is the Bohr model of the atom. And if you remember this model, we know this model focused on having a nucleus in the middle of an atom and having electrons that orbit the nucleus. So this is akin to our solar system where we have the sun in the middle and the planets circle the sun. Bohr postulated a very similar model where the electrons were particles orbiting the nucleus. There's some limitations to this model. The largest one is it really only works for atoms with one electron, such as hydrogen. A more complex and a more accurate description of the atom has to do with the quantum model of the atom. And we will only touch the surface of the quantum mechanics involved here. Really, we're just going to look at the results, and that net result are the electron configurations that we'll see. So a couple things to know. Here in this model, electrons are described by orbitals. Again, that orbital word comes from Bohr, but now we're going to see orbitals can have different sizes and different shapes. And what we're going to see is each orbital is defined by what's known as quantum numbers. And these quantum numbers are what describe the size, shape, and orientation of an orbital. An electron configuration then is really a shorthand notation, and that's going to tell us chemists where all of the electrons are in an atom, what orbitals hold all of the electrons in an atom. So a little bit about our quantum numbers first that define each electron. There are 4 quantum numbers. The first quantum number is the principal quantum number n. And the thing to remember about n, without going into detail, is n is an integer value, so it might be 1, 2, 3, 4, etc. And this is similar to the shells that Bohr had. What we're saying is there's a first shell, a second shell, a third shell, and so on. With each shell, our orbitals get bigger. So the simplest orbital is a spherical orbital. This would be the first spherical orbital. Here's the second, and here's the third, right? As we go up in principal quantum number, our electrons get further from the nucleus because the orbitals get bigger. The second quantum number is what's known as the angular momentum quantum number. Now, the angular momentum quantum number has to do with shape. All right, so this is really a subshell. So we can see the angular momentum quantum number is identified by letters. So we talk about an s orbital, a p orbital, d, f, and then we go down the alphabet. An s orbital, remember this defines shape. So every time we see an s orbital, it's going to be spherical in shape. If we see a p orbital, then we have this dumbbell shape. So this is what all p orbitals look like. All right. Now, every time we start a new shell, we get another subshell. So in the first shell, we have when n equals 1, a 1s orbital. In the second shell, when n equals 2, we have the possibility of a 2s and a 2p. If we go to the third shell, we're picking up another subshell, this 3d, and so on. So every time we go to a different shell, we're getting another subshell of orbitals, and that's going up. So 4s, 4p, 4d, 4f. If we went to the fifth shell, we would add in a g orbital. Again, the angular momentum quantum number defines our shape. So s's are spheres, p's are dumbbells. We can see some other ones we'll see in a second. The third quantum number is the magnetic quantum number, m sub l. And the important thing to remember about this one is this tells us the orientation. So what direction does the orbital point? And more importantly, how many of a given type of orbital are there? So what I mean by that is whenever we're dealing with an s orbital, whether it's a 1s, a 2s, a 3s, there's only one orientation. It's always spherical, so there's only a single s orbital in each shell. However, with a p orbital, there are three different ways the p orbital can be presented. It can go left and right, up and down, or front and back. That means every time we see a p orbital, so there's actually three different p orbitals in each shell that contains p orbitals. When you go to the d orbitals, now there are 5 d orbitals pointing in different directions. With the f orbitals, there are 7 different f orbitals. And you don't need to memorize what the d's and the f orbitals look like. The important thing to know is every time we add a subshell, we're going to gain 2 more orbitals. So 1s, 3p, 5d, 7 f orbitals. The fourth quantum number is what's known as the spin quantum number. And the important point of the spin quantum number is just that electrons can be described as spin up or spin down, all right? And we often symbolize an electron by an arrow, and that arrow can be either down or it can be up. And what comes about from this is what's known as the Pauli exclusion principle, and that says no 2 electrons can have the same 4 quantum numbers. Another way of saying that same sentence is shown here, is that every time we have an orbital, that orbital can hold 2 electrons. And the electrons have to have opposite spin. So one spins up, one spins down. So no orbital can have more than 2 electrons to it. Okay, so let's start thinking about our electron configurations. The goal of an electron configuration is to describe all the electrons in an atom in the lowest energy configuration, or the so-called ground state. So when we look at this, what I'm going to draw here is an orbital energy diagram. So we have energy on the y-axis, the lowest energy orbitals will be at the bottom, and the highest energy orbitals will be at the top. So the lowest energy orbital is the 1s orbital. There's the first shell of electrons. The only thing present is an s orbital, and the first shell can hold 2 electrons because there's one orbital, right? And that orbital can hold 2 electrons, so the first shell can hold 2 electrons. In the second shell, there is now a 2s orbital, and there are 3 different 2p orbitals. So now we can hold 2, 4, 6, 8 electrons in the second shell. The next shell would then contain a 3s, a 3p, and a 3d orbitals for a total of 18 electrons. So again, 18 because each orbital, and now there's 5 d orbitals, contain 2 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals for 18 electrons. We would then go on to the fourth shell and fifth shell, etc. We can see the fourth shell adds our Fs, which gives us 32 electrons, and the fifth shell adds a G, which gives us 50 total electrons. I did not put the fifth shell on our orbital energy diagram. The other thing to take note of is when we look at this, it gets a little confusing when you get high in energy in that the 4s is actually lower in energy than the 3d. So that's a little tricky to think about when we want to understand orbital energy diagrams. But what I hope to illustrate to you is that we can use the periodic table to tell us the order of orbital energies. So we don't need to memorize this diagram if we can read the periodic table. And so what's shown here on this slide are 2 diagrams. The first diagram in this upper left-hand corner, right? This is the orbital energies that we just showed on the previous slide, and how to sort of fill them. And then the second diagram shown over here is our periodic table, again for orbital energies. And so what we can see in this first diagram is this arrow tells you the orbital energy. You'd start filling the 1s, and then you go up and around to the 2s, up and around to the 2p, 3s up and around to the 3p, 4s, and that would be lowest energy orbital to highest energy orbital, and so on. On the periodic table, you can get the same thing, and you see in this first row, if we look across, we have a 1s orbital, and we can see there's 1, 2 atoms, because we can have 2 electrons in the first row, so there's your 1s. In the second shell, we have a 2s and a 2p, so here's your 2s, which holds 2 electrons, and there's 3 different 2p's, so there's your 2p. All right, and then we would go to the third shell where we have our 3s, so here's your 3s, we can see 3p and 3d, then we have our 3p here, but the interesting thing is that the 4s is lower in energy than the 3d, and by the periodic table we can see that, where after we fill the 3p, we'd come down to 4s. So here's your 4s, and then we have our 3d that comes after the 4s, and then the 4p, exactly what's shown in this diagram. So the periodic table can help us with this. Now that we've learned a little bit about the background of electron configurations, please go on to part 2, which will describe how to write an electron configuration.